Thanks, everybody. My name is Dan Bader. I'm a scientist at Columbia University, and I'll be presenting with Abby Sullivan. I'll introduce herself as she's also going to talk to the first two slides here.
Yeah, I work in the Philadelphia Office of Sustainability, but previously worked at the water department in Philadelphia. So I am familiar with a lot of these faces on the call today or in the workshop. So you can go to the next slide. So in seeing this survey from all of you, it seems like a pretty sophisticated group. Probably a lot of these slides up front we can sort of breeze through, but we do want to kind of start with some of the basics. So one of the things that I find challenging, and you guys might understand this, but I think communicating these nuances are really difficult. So I wanted to open with, we see a lot of headlines in the news that talk about a flood being blamed on climate change or really linking climate change to a specific event. And I think that that's challenging because for many years, we always talked about how, climate is an average over time and weather is an event. And so I feel like this gets really confusing for people. And then the other thing is that we've always had these extreme events. It's not like we didn't see extreme storms and hurricanes and flooding in the past. So I wanted to pass it to Dan to sort of dive into sort of some of the nuances and things with attribution. So what is climate? What is weather? What are we talking about?
Yeah, I think as Abby is kind of queued up here, it's really fundamental to understand the distinction between weather and climate when we're talking about extremes that we're experiencing now, have experienced in the past, and will continue to see in the future. The analogy that I'm going to use here to explain the difference between weather and climate, and we use this expression in the field that weather is what you get, climate is what you expect, is take a moment to think if you have a dog and you're taking your dog on a walk down the sidewalk. The dog probably will meander from one side of the pavement to the other as it continues forward. But the path you take while walking the dog will most likely be fairly straight. The variations in the path that the dog takes are what we'd be describing as weather. Those are kind of the short-term variations are in our atmosphere on a day-to-day basis. When we average those conditions over time, that reflects our climate. And in the field of climate science, we like to use 30-year averages. So if you listen to the weather report in the morning and hear that the average temperature for October 17th, the high temperature average is 75 degrees, sort of warm for the Northeast, but just going with it, that reflects, let's say, the last 30 October 17th average together. The actual high we experience, let's say it's 68 degrees today, is the weather event that we get. And in the wake of the climate extremes that we're seeing, we're using here an example from the extreme rainfall event from about 2 weeks ago here in New York City, where some locations saw upward of 8 inches of rain. It's important to understand this breakdown of detection and attribution. The first thing we have to do is detect to see if there's a trend, finding out if something is out of the ordinary. Is this a one-time event, or has this been a continuation of trend over time? That would be what we look at in detection. Then we move to attribution to try and understand what the cause of that trend is. Is it in fact a natural cycle, and so North Atlantic oscillation that's causing these changes, or can we link it strongly to human activity? In the context of the extreme of rainfall events that we've been seeing and probably will be discussing over the next couple of days, we know that, as was described a bit earlier, a warmer environment is a wetter environment. We have the greater likelihood of having these heavy rainfall events. They have been increasing over time in the Northeast, upwards of 70%. So we can start to make those connections there. So a key component is understanding weather and climate so we can have this conversation of what these events that we're experiencing are like and what their cause may be. So I'm going to hand it back over to Abby now, who's going to introduce what models are and how we start to use models to understand climate change.
Okay, next slide. We can skip this. I think everybody on this call probably has an understanding of what models are, but they are the simplification of reality where you're trying to use mathematics and statistics to sort of model the physical world. So I love this example. I think for a lot of people that aren't technical, models are sort of a black box. And so I love to go back to the 1940s when people literally built physical physical models to represent something in reality. And so here's an example where the Army Corps built a model of the Mississippi watershed, and they could test, interventions, flood solutions like a levee or a dam, and see how that actually impacted the hydrologic and hydraulic flows through that system. And so this, I think, helps people understand that when we're talking about models, we're literally talking about, a model of the physical world. So you can go to the next slide. Here's just some additional images of this. This scale model was over 200 acres. It actually became like a tourist attraction. It did shut down eventually. You can go to the next slide. Because today we don't build those physical models anymore. We use computers to do the same purpose, and it's really sped up the process. We have lots of calculations and formulas that can be used to represent the physical world, and they're simulated with the help of software and computer systems. So that's sort of just a basic, here's when we're talking about modeling, we're, it's very similar to what we used to do in the past, where we built a physical model to represent what's happening in a larger system. Next slide. So global climate models, we do, a lot of this work that we do is based on using the output from global climate models. So just a quick overview of what they are. They attempt to describe the full three-dimensional geometry of the Earth's climate system. They solve equations of physics and physics and chemistry, and they apply that to the atmosphere and its components and try to basically understand the interactions in space, both going up into the atmosphere and also down into the ocean. And they have advanced significantly over the years. So you can see there that timeline across the bottom. They really used to just be based on the atmosphere. Now they include the ocean, hydrologic cycles, ice sheets, biosphere, carbon cycles. They're getting more and more sophisticated as time goes on. You can go to the next slide. As you can imagine, go back one. So as you can imagine, if you work with models, they're very, there's a lot of information. You have to have a lot of computing power. And so to represent the entire climate is very, very intensive. It takes a lot of computing power. And so there's really only a handful of modeling centers around the world. Technically, I think there's over 40, but a lot of them are based in the same cities. And so there's really this exercise called the Coupled Modeled Intercomparison Project, or CMIP. And that's where all of these modeling centers around the world that have the capacity to model the atmosphere and the ocean and our climate, they get together and they agree on a set of scenarios to run through the model into the future based on how many emissions we're going to have in the future and other socioeconomic scenarios. And they then compare the results. So this is how we sort of get our projections, and how we have confidence in the projections is that it's not from one source. We're actually sort of comparing globally what some of these top centers in the world have their model output say. So I'm going to pass it back to Dan now. So how do we use these models, and how do we understand how their output is used to understand climate projections?
So we're going to start from CMIP and now kind of work our way down from the global scale climate assessment and the global climate models to the local scale. Because ultimately what we're looking for when we're planning is the best available local information. And now, while there are constraints of getting that with the climate models, there is a process that will take us there. And it starts, in most cases, working with the global climate models from CMIP. So CMIP, the goal of the project is to better understand past, present, and future climate change. So it's not just about the future. Climate models can offer some insight into the past and present, and we'll take a look at that in another slide or two here. This research effort is coordinated by the World Climate Research Program. And within CMIP, the activity that is focused on the climate models that we'll use for our projections is scenario map. These projections, Abby just hinted to, and we'll talk in a minute here, are based on scenarios of future greenhouse gas emissions and land use changes. In those mathematical and physical models that represent our climate system, the number one driver, or the number one input that we place into them are these scenarios of future emissions. For CMIP, and CMIP6. These are the latest climate models available to scientists. They're part of the IPCC, the Intergovernmental Panel on Climate Change. It's their 6th assessment report. There's a new framework that can be utilized, and these scenarios are known as the shared socioeconomic pathways. We'll refer to them as SSPs. The SSPs are based on 5 different narratives which describe alternative socioeconomic developments. This takes into consideration things like sustainable development, regional rivalry, the development of fossil fuels. And for each of these SSPs, for each of these 5 narratives, there are a number of different radiative forces targets that can be met at the end of the century. Radiative forcing really is a measure of the energy imbalance, and a positive radiative forcing, which we experience, is what's leading to warming. So that measure of radiative forcing or energy imbalance is what these scenarios target towards the end of the century. The scenario MIP experiment developed 9 scenarios of future greenhouse gas emissions. 4 of them update the RCPs, which were the emission scenarios from the prior CMIP assessment, CMIP 5. If you're familiar with RCP, let's say 4.5 or 8.5, and look at the figure and see SSP 2-4.5 or SSP 5-8.5, the 4.5 and 8.5s are the end of the century radiative forcing. The trajectory which the scenarios take to get to those points may differ, but it's the same level of energy imbalance, let's say, at the end of the century. There are also 5 new scenarios here that fill in some of the gaps that were not previously covered by the RCPs. Depending on the scenario you select, the number of models that are available do change. There also needs to be consideration when you're selecting scenarios. Do these pathways really represent a trajectory that either we're on now or could potentially get at? So if you take a look at that low end scenario, can we really reduce our emissions that rapidly to be on that pathway? And alternatively, the high end scenario, is there evidence to suggest that we're tracking along that way, or are we making enough adjustments to say, hey, that may not hold to be in the future? Just a quick comparison of how these models have advanced over time. CMIP6 models have a higher spatial resolution. The grid boxes, so the little squares that they break the globe into and run the equations over, have improved. They're in the order of about 75 to 75 miles, let's say. A great improvement, let's say, from some of the first IPCC assessment processes. They have more advanced characterizations of key components of the climate system. There's so many processes, so many interactions that are taking place between the water cycle, the carbon cycle, the cryosphere, the atmosphere. We're using math and physics to represent them. Of course, we can't represent them all perfectly, but we can improve our understanding and representation of them with time. This is the most advanced set of models that we have. There is a measure known as climate sensitivity, how much the model projects average temperatures to warm under a doubling of greenhouse gas, of carbon dioxide emissions. Some of these models are warm. They have a hot model problem, as it's being deemed across the scientific community. And in some cases, there's an argument to say that these models with that higher climate sensitivity could be less reliable or valuable than others. So it's up to kind of the user the information to decide whether or not they want to kind of select those models in their assessment, include them with the relevant caveats. When we're doing climate assessment, we want to include a broad range of models and scenarios to look at a range of possible outcomes to present our results across. Like I said earlier, models aren't just used for the future. They can help us validate and understand the past. On this chart, the black line is the actual observed temperature time series on the globe, observation. So that's what actually have happened. What we can use our models to do is replicate that. Can our models simulate within close proximity of what we've actually experienced here? And the only way we get our models to replicate what's actually been observed is when we include both natural factors and human factors. If we only include natural factors, volcanic activity, changes in solar cycles, the model's time series does not match what's been observed. This points to that human activity isn't interfering with the climate system. And in order to best represent our climate system with the models, we have to include those human factors as well. The fact that the models do line up pretty closely with the observations lends some credibility to them. The models do a good job with predicting on a whole what the climate system should represent. When we move now from the higher level of kind of globally, how can we use these projections locally? What are the applications we can have? How can we use the data from the GCMs kind of for our own planning purposes? The way we bring down information from the global to the local scale is known as downscaling. There are two primary ways we downscale climate information. Dynamical downscaling, which in large part is just using a regional climate model, takes the global climate model and runs it over a smaller, higher resolution domain. I don't work very much with dynamical downscaling. The technique that I'm most familiar with is statistical downscalings, which uses historical relationships between the large and smaller scale to bring the information from the GCMs to the local level. There are pros and cons with each of these methods. As I said, I'm most familiar with statistical downscaling. One advantage of it, it's pretty simple from a computing standpoint to be able to use and work with a large number of models. And the results from it are widely accepted by stakeholders, utility managers, policy and decision makers for their applications and needs. However, in some cases, statistical downscaling, it relies on historical data. And because it relies on historical data, the patterns in the historical period would be present in the future, which we know may not be the case. With dynamical downscaling, you get a better representation of some of these smaller scale climate processes, things like mountain ranges and the interaction of winds moving either over or off of mountain ranges, sea breeze or land breeze interactions. The dynamical models can simulate at that smaller spatial domain. However, the drawback in using them is that they are very, very computationally expensive, or a lot of not only physical infrastructure for the computing, but it takes a lot of time to run these models. The data sets are also limited in their availability as well. What do results look like? How are they being used? To answer this question, we're going to preface it with there's a tremendous amount of information out there, and it continues to grow as kind of climate assessment advances. There are numerous data tools, some of which Abby will highlight in a bit here, where you can go and download for a given point climate risk information. I'm just highlighting some report that I've done through my work with the Consortium for Climate Risk in the Urban Northeast, which is a NOAA CAP RESA project that I work with. We've worked with New York City, New York State, and the city of Philadelphia extensively over the years on their climate assessments. These are just a sample of the work that's available for the US. You have the National Climate Assessment and the Interagency Report for sea level rise, you have climate explorer tools. We're presenting our methods. There are many different ways. Just use this as an example of how we take that global information and move it to the local scale. And then that local scale is then integrated into planning. For our projections, we break them down into mean changes, so changes in mean annual temperature and precipitation. This is used using statistical downscaling, a very basic approach known as delta method, where you compare model results for the future to that model's base period. We can look at annual, monthly, and seasonal changes. And when we present our results, we look at different percentiles. So we take outputs from 35 GCMs from 2 of these different scenarios. We have a total of 70, and we're presenting the results across those 70 outputs. We also use an ensemble average for each of the different SSPs. For our projections of extreme events, such as hot days or extreme rainfall, we're using another statistical downscaling technique known as quantile mapping. And what that does is it looks at how a given percentile changes. So let's say you have the 17th percentile. For the 17th percentile in the observed data set, we look at the models to see how the modeled 17th percentile changes in the future. So if the 17th percentile changes by 2.5 degrees, we take 2.5 degrees of warming and add it to the 17th percentile in the base period. What we get is a time series, a synthetic time series of daily events for the future from which we can compute our results. Again, we're presenting across different percentiles a smaller number of GCMs just because not all the GCMs have daily outputs, and we use the daily GCM data here, whereas for the mean changes, we're using monthly outputs. For things like tropical cyclones, snowfall, extratropical storms, nor'easters, we're not able to rely on the climate models directly. So what we can do is offer qualitative projections based on both literature review and expert science judgment. And we can create these, what we're referring to as descriptive scenarios, which really reflect what a worst case storm may look like in the future. Let's say a hurricane, under these different change conditions, what we could be experiencing in the future. We can offer projections that way. For sea level rise projections, there is a tool now from the IPCC where you can extract the data directly for a given point, both just grid box, or they have it for certain tide gauges as well. We use 3 of the scenarios. They have various confidence. The low confidence scenario is to represent a case where there would be a greater loss of land-based ice causing higher sea level rise. Our stakeholders are interested in that kind of low, very low probability, but high impact event. So we include that scenario in our results. We take the results directly. We've only interpolated them a slight bit to pull them to the middle of the time period. They're available at the start of the decade. We usually use the midpoint of the decade since we like to average over those 10 years. We create a distribution and then present our results across those outputs. That again is just our method in-house. We vet it with other experts, but there are multiple ways to go forward. Some key considerations as you start thinking about using new data. There's an issue of continuity versus the latest science. Some of our stakeholders are really locked into the scenarios that they are familiar with. Whereas the latest scenarios say RCP or SSP 8.5 may overestimate emissions and how we're kind of tracking. How do you make adjustments? How do you go about with the various amounts of information? What's the best way to pick? Downscaling, displaying results is a continual evolving process. This requires a lot of back and forth between us scientists and the stakeholders that we're working with. And the results can change over time. Usually, the results differ from assessment to assessment within the uncertainty ranges that we'd expect from their models. But in some cases, there is a difference. How do we explain that difference? And what are the implications on the planning side when there is such a difference? So with that, I'm going to wrap up and I'm going to pass it back to Abby here, who's going to talk to you about how we actually apply some of this information.
Great, thanks. Yes, if you go to the next slide. So I'm going to start off by talking about a few sort of key takeaways that I've found in working with this climate information and how you apply it when, you're trying to solve a question. And also some tools that you might be able to use. And so the first one I want to point out is that I think with the update with CMIP 6, one of the really key changes that I think has made it much easier for practitioners to understand is that they're now really doing this link between the SSPs, these emission scenarios, and temperature at the end of the century. And to me, I think that's way more sort of it's something people can grasp way more than a radiative forcing amount at the end of the century. And so here you can see what this is the global climate tracker. This is their sort of the global mean temperature thermometer. And it basically looks at where we're headed right now with current policies and actions. And based on their estimates and their modeling, we should be on track to see about 2.7 degrees of warming in 2100. As you guys are aware, we're trying to limit the warming to 1.5 degrees in the Paris Agreement. So that's quite off from the target. So based on current policies and actions, that's where we're headed. You can see that sort of range there in blue. So there is a lot of overlap in sort of what temperature we might see at the end of the century and the outcomes of these SSPs at the end of the century. So, but you can kind of see that right now, based on policies and actions, SSP3 7.0 and SSP2 4.5 are really the ones that fall within that range. So to me, that helps practitioners understand that these are potentially the likely scenarios you want to use if depending on your risk tolerance and a few things that we're going to talk about in more depth moving forward. But those are really the scenarios that are likely to sort of fall within that 2.7 degrees C range at the end of the century. 2030 targets only. Now, this is a bit more optimistic. This is saying if all the countries meet their nationally disclosed commitments, which we are not on track to do. There's hardly any countries that are actually sort of on track to meet these targets, but, you know, hopeful that that could change in the coming years. But if we were to implement all of those, you know, meet all of those targets, we're really talking about almost perfectly aligning with what SSP 2.4.5 shows the warming to be at the end of the century. And then, you know, you can see more and more optimistic scenarios. But I think this framing of these emission scenarios and the amount of warming that we're going to see at the end of the century is a really useful way for practitioners to sort of grasp and understand what this is saying. You can move on, Dan. Next slide. So I did want to point out that, you know, Dan mentioned a few of the resources for accessing climate information and where you can go to actually sort of either download the raw downscaled information, or you can get some climate service information with statistics and things like that. There is a ton of these climate services out there. Another one here is the Climate Explorer. So this is a place where you can go in and put in any county in the United States, and you can get these outputs, statistical outputs about certain parameters for climate, for the historical weather, where these sort of thresholds, even things like high tide flooding, how will that change moving forward? So there's a lot of information that's out there. Another great tool I don't have a slide on, but I think the Partnership for the Delaware Estuary has put out some really amazing reports recently that sort of talk about climate in the Delaware Basin. And so I think we're going to have probably more presentations that sort of focus more on the basin scale, but I think that's another really great resource for people working in Delaware River Basin. Next slide, please. I think Dan mentioned this, but there are really these sort of two main sources for sea level rise information. So one of the great improvements with the 6th assessment report from the IPCC is that they actually provide localized sea level rise projections at either a tide gauge or at a 1 degree around the coastline of the United States. So there's actually a NASA tool that allows you to go in, select your location or your tide gauge. You can get all of the information, all of the different scenarios for that location directly. There's also an interagency report that came out from the United States. This is supposed to be sort of the US sea level rise scenarios that are for use in planning. And these, they're different. So there's these, you know, and this is one of the challenges that I think we just have to admit is that there's all these different climate services, and it's really challenging to know which one do you choose and why. And so, you know, there are differences in the approaches here, but I will say that the interagency sea level rise scenarios, they tried to keep the scenarios somewhat consistent with earlier reports that came out from the US government. So if you were already using those sea level rise scenarios, it's supposed to provide some continuity so that even though the science is being updated, so we understand differences in the probabilities of these scenarios occurring, you can sort of try to keep the same planning scenario moving forward. You go to the next slide. Another tool I wanted to really quickly point out is this really amazing tool from NASA. I think NOAA has one as well. Again, this, you know, issue of like two different federal climate service providers creating a very similar tool using slightly different information. It's really challenging for practitioners. But this tool is really amazing. You can go into locations around the United States on the coast, and this is, again, sort of a coastal tool. But this shows you that today, let me quickly just explain what this is showing. The blue line there, the dark blue line is the 50th percentile. So kind of what we think is likely to occur is the amount of projected flooding days that meet that flooding threshold. So in the top center, you can see the user can input any flooding threshold they want. So you could go and look at the elevation of a critical pumping station at your wastewater plant or part of your system, and you can create that flooding elevation threshold above mean high or high water. Then you can input different sea level rise scenarios, and it will tell you how the projected flooding days over time will change by 2100. So here you can see if your flooding threshold was 1.84 feet above mean high or high water, today in 2020, we're seeing about 17 events. However, if we use the intermediate low sea level rise scenario, which is probably an underestimate of what we're going to see by 2100, so 2.42 feet, just simply raising that starting water level will make you reach that flooding threshold 307 times a year versus that 17 today. So we're not talking about, like a major storm event coming through. We're simply talking about the changing flood probability of sort of a, whatever threshold you end up choosing. You might choose something extreme, but it lets you input this information and really shows you that change over time. Okay, you can move on to the next. Another resource I wanted to point out, this was really made for that interagency report, but I think some of the information could probably be applied to the IPCC sea level rise projections as well, but there is an application guide now. I think a lot of these sort of federal reports about climate are very dense. They're kind of full of jargon. It's very hard for practitioners to really read through it and pull out the pertinent pieces of information. And so this application guide, this is really one of those great examples of co-development. So there was a group of practitioners and boundary folks that got together and made this application guide. It was reviewed by the NASA Sea Level Change Practitioner Board. So there's a lot of really great information in how to understand the uncertainty in sea level rise, how that uncertainty is different for the different scenarios, more information about the likelihood of these scenarios being exceeded in the future, and tying it again back to air temperature changes. So that's another great resources. On all these slides, which will be shared, there are links so that you guys will have information to this. And I think we're going to also send some resources after the workshop. So next slide. So some high level considerations and limitations. Dan's touched on a lot of these, and even some of the earlier presentations have touched on these as well. So I can kind of quickly go through these, but we definitely have the most confidence in temperature projections. Extremes are not captured well by the GCMs, particularly for precipitation. There are resolution challenges for precipitation, and I'm going to talk about that a little bit more in depth with like case study example in a few slides, so I'm not going to talk about that here. And as Dan mentioned, there's these new emission scenarios, or they're socio, it's not just emissions, there's also these different sort of socio pathways that get us to these sort of end of century scenarios. So there's new scenarios, and one that I wanted to mention is this SSP 3 7.0. I think in my first slide, I made the point that where we're headed today, based on policies and commitments that are actually happening, really falls within the results of this SSP 3 7.0 and SSP 2 4.5. And so we, as the City of Philadelphia in the Office of Sustainability, we're updating the climate science for the city. And we, so Dan, in his, the way that they did it for CC Run, they chose, I think it's really smart. A lot of practitioners want to have consistent information. So stuck with those two scenarios that were also part of CMIP 5. We decided that even though it would be adding an entire new scenario, we wanted to look at that RCP 4.5 scenario, the updated version, 8.5, and also this new SSP 3 7.0. Dan sort of touched on this, but there is a lot of information out there about how RCP 8.5 is really not business as usual. When I started working in this space a few years ago, 2016, that was really considered business as usual. I think we even had slides that said RCP 8.5 is business as usual, and that's really not the case. It's actually a worst case scenario. It involves things like ramping up coal production and population explosions, and it's really not business as usual. That is not to say we shouldn't still consider planning with it. I think there's many questions and many applications where we still want to consider a worst case scenario. So it's not to say it isn't a worthwhile scenario to look at. It's just understanding the differences between these things. For sea level rise, we're very confident in the direction of change. And especially through mid-century, we've definitely made a lot of progress, I think, in these sort of near-term to mid-century projections. But after 2050, that uncertainty is still extremely high. Dan mentioned that they now include, CMIP6 now includes 2 low confidence scenarios. IPCC was greatly criticized in the past. They would really only include model results that had very high confidence physical processes and understanding. And so they really kind of excluded any modeling that included some less certain physics and processes associated with ice sheet collapse. And so there was a lot of sort of critique that you're really not showing the full range of what might be happening. And so as he mentioned, as Dan mentioned, there are these 2 now low confidence scenarios where they are including results from some of those models that include some of those ice sheet processes that are still very uncertain. Yeah, I think, another really key thing to me, and sorry, this is a bit focused on sea level rise. That was really more my area when I worked at PWD. So hopefully this is useful information for folks. But a best practice that has emerged now, and this is really highlighted in that interagency report, is that for near term, meaning, today through the 2050s, mid-century, a best practice is to really use the scenarios that most closely align with observed extrapolations. And what I mean by observed extrapolations, and that report goes into much depth, and that application guide talks about this extensively, how to understand that, but is you look at the last 20, 30 years of your sea level rise trend, and you extend that trend out to the 2050s, and you see which of the sea level rise scenarios that aligns with. So really for mid-century applications, it's very unlikely, if we're trending with something, that in the next 30 years, we're going to wildly go off that trajectory. And so I think that's emerging as a best practice as well. All right, next slide, please. Another thing I really wanted to touch on, I have been working in this space for a while, and I still see people that are also like practitioners that have been working on adaptation for years. I still see them get confused by these probabilities. I think it's, we talk about 10th percentile, 90th percentile. And so I kind of want to unpack that a little bit here. And this is an image that came from a report that Dan worked on. So I think this is one of the best visuals to explain this. So if you look at annual temperature change across the bottom, and then you can see the number of model-based outcomes that sort of get you to that temperature change. We can bin those results, meaning how many models say that we're going to see between 1 and 2 degrees of temperature change? How many models say we're going to see between 2 and 3 degrees? So on and so forth, all the way up to 10. And so you get that sort of model distribution of how many of those GCMs agree that we're going to see between 4 and 5 degrees of annual temperature change. So that's where you start to see there's this range of model outcomes. And when we're talking about the 50th percentile, or those models in the middle, that's where we see model agreement. I almost wish that we didn't talk about them as probability at all, and we just talked about it as being model agreement. So even though, yes, these models in the middle, about half of them say we're going to see less, about half of them say we're going to see more, but that is where there's the most model agreement. These tail ends of the distribution are really where there's almost like an outlier, where 1 or 2 models said, hey, we think if you run this scenario, we're going to see this really high annual temperature change. So it's not to say that model may be right? But we have less confidence in that because there's not a lot of models agreeing that that's the outcome we're going to see. And so IPCC, they used to only really show the middle 17th to 83rd percentiles. There's been really a sea change in recent years where some folks, and this has been, I think, largely driven by Bob Kopp at Rutgers, where, the idea is to give practitioners more information, to show you more of that distribution, but to really understand what those percentiles mean. So I think, the idea is we should be able to see that there's a few models that show we might see 8 degrees of annual temperature change. we don't have a lot of confidence in them because there's maybe only 5 that agree versus the 25 that agree we're only going to see 4 to 5 degrees. But I think people feel like allowing people to see that tail end distribution, but understand that there's really low agreement. It's not likely to occur, but it could occur. So, you know, letting the practitioner decide and understand that each application has a different risk tolerance, adaptive capacity, and you may want to plan for that worst case scenario. All right, next slide. And I see we have 5 minutes left. I feel like this is good. So using a risk-based framework can help you deal with uncertainty. So when you do have to make decisions, I think Dan mentioned that best practice is to always screen your risk against multiple scenarios, right? We really need to understand, we don't know what the future is going to be. So screening against all these different scenarios is the best practice. However, if you're running a model, oftentimes you don't have the resources to run 6 different scenarios. You might have to choose 1 or 2. And so how do you actually make these hard decisions? You can use this risk-based framework where you consider the criticality, the risk tolerance, the useful life, and the adaptive capacities. And that should help you sort of, you know, there is no perfect guide that tells you what you should then use, but considering these components, I think really helps you sort of make those decisions in the face of all that uncertainty. So for example, if you were, you know, a transportation professional and you're going to design a road and you want to consider climate change, you may end up going with what you think is a most likely scenario because the criticality of that road, you know, it might be a critical road if it's an evacuation route, but it might just be a surface route that's not a critical route. You could consider the risk tolerance. Again, water might be able to touch it if it were to flood and it would be fine after the water recedes. The adaptive capacity might be low because you can't really raise the road. But again, you know, these are the things to consider, whether you want to use sort of a worst case scenario versus a more likely scenario that's going to occur. Something like a water utility tends to be very critical. We're talking about drinking water for folks, has a low risk tolerance, has a long useful service life, right? A lot of these infrastructures are put in place for 50 to 100 years. And then the adaptive capacity is also very low. For example, you might be able to change your storm sewer size, the size of that pipe, but it still has to connect to the rest of the system that's undersized, right? So the adaptive capacity, plus it's underground, it's really hard to reach. So these are all the considerations that you might need to think about when you have to make those hard decisions. Next slide. Julie kind of presented this slide. So I think the way you approach how you use this information really changes depending on the answer or the question that you're trying to answer. And I think a point here is that, you know, I think to answer a lot of these questions, you can't just go to a climate service provider like NOAA or NASA and get all the information you need. You need to have staff or a consultant or somebody that has that technical understanding of how to work with that downscale climate information to get you different statistics, to do a different assessment using that information. So next slide. So I'm just going to quickly touch on like 1 or 2 examples. So let's say as a water utility provider under the Safe Drinking Water Act, there's 2 regulations that kind of work against each other. One is for chlorine residual, right? You have to have your disinfection that goes into treated drinking water last throughout the entire system, right? So there's regulations that say you must meet this chlorine residual target. You also have a regulation that says you cannot have disinfection byproducts above a certain amount. A disinfection byproduct is something that forms that's carcinogenic when that disinfection reaches something called a precursor. This is naturally occurring organic materials in the water. So these 2 things make it really hard to meet regulations in the summer months because in the summer months, our water temperatures are hotter, more of that natural organic material forms. And it's also when water is warmer, that chlorine or your disinfectant breaks down faster. So you have to use more of it. So there's more of the precursor and you're using more of the disinfectant. And so it's harder to meet both of those regulations. So as you know, a utility provider, you might want to know with climate, Will those summers start earlier and end later? Are there critical temperature thresholds in the water, or, you know, once we pull it into the treatment plant, are there critical temperature thresholds that we want to assess under future scenarios? To do that, you might have to first understand what's that relationship between air temperature and source water. And so these are the type of assessments where you're going to need to actually work with that downscale climate information and potentially do more statistical analysis or assessments, or even use that information models to answer your question. All right, next slide. And just one more example, and Julia touched on this, but a lot of the work that we do as water utilities, or even, you know, looking into flooding, we use H&H models. And these models really need high resolution information, and that's talking about temporal resolution. So the GCMs, even when they're downscaled, are only going to give you a daily output. It's going to show you the maximum precipitation during the day and the minimum. And so we really need hourly or sub-hourly information. This is a major, major hurdle to get over. There's also spatial resolution issues as well. So we can see that the GCMs really show us an unrealistic rainfall pattern. So it's something called the drizzle effect. So in Philadelphia, we see the GCMs say we have a little bit of rain every single day, as where we all know, living in this region, we get periods of dryness and then these intense, you know, thunderstorms in the summertime. And so we really have to do work. We have to take that downscaled information and do further sort of massaging and tweaking and using different methods to make that information actionable. And so PWD has done a lot of work in this space, as has CC Run. I linked to some workshops there that CC Run and Marisa, another Risa from NOAA, sort of put together, and linked to some videos and reports that help you sort of address these issues that we come across. All right, next slide. I see we're at time, so I think we'll just end it there. This is just further making that point that, you know, the application and the context matter. And I think just one point I'll make here is that I think there's starting to be a lot of guidance on how to use these projections when it comes to flooding of surface and built infrastructure. But I think when it comes to things around water quality, it's way less certain, and there's not much guidance. And there, we'll just go to the end. Thanks.